Hello, everyone. Welcome once again to our series on strength of materials. Today we are looking at Deformation of Bars by Axial Loads. Deformation of Bars by Axial Loads. Kindly subscribe, like, share, and leave your comments and suggestions at the comments section. Let's look at our question today and see how we are going to solve that. Good. Two solid cylindrical rods, AB and BC, are welded together at B and loaded as shown. AB is made of steel with modulus of elasticity 2000 times 10 to the power 6 KSI, and BC is made of brass with modulus of elasticity equals to 150 times 10 to the power 6. Sorry for the STC which is there. This is not supposed to be there. Sorry for that. This is not supposed to be there. Good. If D1 is equal to 2 inches and D2 is equal to 3 inches, determine the displacement at A and B. So this is our diagram. Let's look at how to solve for this problem. Good. When you are given any problem on axial load to find, you are basically going to divide your complex shape or your complex bar into sections, which will help you to be able to calculate the deformation at each of the sections. There are three things which are going to guide your division. There are three things which are going to guide your divisions. The first one is area. So if it is cylindrical, then once the diameter changes, the area is going to change. And the second one is material. The second one is material. Material. Sorry for that. The next one is material. So once the material property changes, then the amount of deformation is also going to change. So the next one is material. And the last one is, so the material is related to E. And then the last one is force. So anytime you encounter a new force, then you need to also section the figure. Looking at what you have been given, this portion here is supported, so we cannot start our analysis from here. This is fixed. This is the free end. Therefore, we can start, always remember to start your analysis from the free end. Now, what you do, we start from point A. As we move along, anytime there's a change in diameter, we need to divide that section. Anytime we encounter a new material, we also need to divide that section. And anytime we encounter a new force, we need to divide the section. So as we start from the free end, which is A, you find out that you are not encountering any force. Once you reach here, you have encountered a force, and you have also encountered a new diameter. Therefore, we need to divide that section. We need to divide that section. Then, so this from A to B is going to be one section since you have encountered a new force or a new diameter. Then from B, as we move along, you find out that we encounter another force here. And we said that once you encounter a new force, you are going to get a new session. So this will be probably first session, this will be our second. And as we move from this point onwards, we don't encounter any different diameter or any different force. Don't forget that the material for this and that was changing, but because where the material, we are entering from one material to another, at the same point, you have the diameter changing and force applied. So we are going to take it as only one division. Now we have been able to divide our complex structure into three main sections. What we are now going to do is to calculate the internal forces in each of the three sections we have. We are going to calculate the internal forces. So first of all, we draw the free body diagram for each of the different sections. So we can draw for section 1 as this. When we draw for section 1, we know that this side is 9 pips. This is 9 pips. Good. And what we cut, this is the section 1. So when we cut the middle part here, then we say that to every action, there is equal and opposite reaction. We can call this P1. Once we do that, we can say that we can use our equilibrium equations. From here, we can say that any force which is going to the right is positive, and any force which is going to the left is negative, and any force which is going to the right is positive. So from here, the 9 pips is going to the left, therefore we have 9, and this P1 is going to the right, minus 9 plus P1 to be equal to 0. And from here, we can say that P1 will be equal to 9 pips. Okay. Good. We can also draw our free body diagram for the second session. But take note, though the second section is from point B to this point here, we can refer to it as B prime. But when we are considering the internal forces in the member, the internal force from B to B prime is affected by all these forces which are here. Therefore, in drawing the free body diagram to determine the internal force from B to B prime, we need to include all these forces here in our diagram. Therefore, our diagram is going to look like this. We have this section here like that. We have this section here. And we are encountering a new diameter. We can draw that like that. So this is A, this is B, this is B prime. And we have 9 at this side. 9. We have one force applied here with a magnitude of 12. We have another also applied here with a magnitude of 12. Then the internal forces, we said that to every action there is equal and opposite reaction. Therefore, the internal force will be pointing that way, and we can refer to this as P2. In the same way, we can draw the free body diagram for the third section, which is from B prime to C, where we cut through the middle or wherever you want to cut. So for that matter, for the third section, our free body diagram is going to be like this. We're encountering a new diameter, and this is, let's say that this is our B, this is our A, this is B. We have B prime at this side, this is B prime, and this point is C. We have a force of 9 at this side. We have a force of 12 at this side. 12 pips. We also have another force at this side, that is also 12 pips. And we have a force applied at B prime like this going this direction, and that is 5. So our internal force will be here. We can call it P3. So from this and that, we can be able to determine the value of P2 and P3 from the different free body diagram. So from here, we can see that the 9 is going to the left, and that is going to be negative 9. This 12 and this 12, they are all going to the right, so they will be positive. You can call them plus 12, plus 12. And we have our P2 also going to the right. P2 will be equal to 0. From here, we can make P2 the subject. So we can say that P2 will be equal to 9 plus 12 plus 12, which will give us 15, but we send it to the other side. So we are going to get negative 15, which means that that internal force is in compression. It's in compression. And we come to this side also. At this side, we can also write our equilibrium equation. The 9 is going to the left to be negative. The 12 is going to the right, positive. Sorry for that. Yes. So we said that the 9 is going to the left, which is going to be negative. The 12 is going to the right, positive, positive. And we have our 5 going to the left, minus 5. And we have P3 going to the right. So we can write plus P3 should be equal to 0. And from there, we can say that P3, when you do the math, you find out that P3 is equal to negative 10 kips. Negative 10 kips. Then from here, once you have been able to determine the internal forces in each of the sections, what we are going to do is that we can calculate the deformation for each of the sections. You can calculate the deformation in section 1, the deformation in section 2, the deformation in section 3. So we know that the formula for is going to be delta is equal to the summation, since we have 3 different sections, summation of Pi, Li over AI, EI. And from there, we can calculate the deformation for each of the sections. Therefore, for A to B, this point is A, this side is B. So from A to B, from A to B, we can say that delta AB will be equal to T. A to B, we have P1 is the internal force there. So we have P1 L1 over A1 E1. So from here, we can see that our deformation will be equal to, we know that P1 is 9 kips, and kips is pounds. So it's times 10 to the power 3. So we are going to get 9 times 10. 9 times 10 to the power 3 times the length of the section. The length of the section from A to B, the length is from this point here up to this point. The length is from this point up to, from this up to that point is 19. That is the length of the section. So we are going to get times 19 over the area. We know that it is cylindrical in shape, so the area is going to be pi d squared on 4. So from there, we can say that our area is going to be 3.142. Pi is 3.142 times the diameter. The diameter of that side, we are told from the question that d small d1 is 2. So we have 2 squared over 4. And the modulus of elasticity was given as 200 times 10 to the power 6. But don't forget that it was given in KSI. And anytime you are given in KSI, you change to, anytime you are given in KSI, you make sure you change to kilopounds. You change to kilopounds. So you have times 10 to the power 3 again. And from indices, if you have times 10 to the power 6 times 10 to the power 3, you add the powers. You add the powers. So the whole of this will give us times 10 to the power 9. And when you do the math, you find out that the deformation of that section is going to be 2.721 times 10 to the power -7 inches. That is the deformation in the first section 1 here. And we need to calculate the deformation in the second section, which is B to B prime. So we can say that delta B to B prime will be equal to D1, D2, L2, that is section 2 over A2, D2. And from there, we know that the internal force in section 2 was P2, which is -15. So we are going to get -15 Gibbs times 10 to the power 3 times the length of the section. Take note, the length of the section, you will not include this 19. The length of the section is only from B to B prime. It's only from B to B prime. Don't include the 19. It's only from that section, B to B prime. The length is what we are considering. So here the length is 16 over area, which is 3.142 times the diameter at that side. We were told that the diameter is 3. So we have 3 squared over 4 times the modulus, which we are given as 150 times 10 to the power 6 times 10 to the power 3 because of the KSI. Don't forget the KSI. So from there, we can get our deformation in BB prime. When you do the calculation, the deformation for BB prime will be equal to -2.263 times 10 to the power 10 to the power -7. -7 inches. So we have been able to calculate the deformation in section 1 and section 2. Now let's also calculate the deformation in section 3 using the parameters given. Let's calculate the deformation for section 3. Sorry for that. Allow me to clean the side so that we can be able to use the space to do our calculation. Good. Let me leave the test session so that you can see the diagram very well to calculate this deformation. And we calculate the deformation for the test session using the same formula as we have described in calculating the other sessions. So we can see that delta for B prime to C will be equal to the force, the internal force, which is P3. We have already calculated that L3, the length of that section, E3. So from there, we can say that the deformation is going to be the force, which is -10 times 10 to the power 3 times 16 over the length of the section. This is 32. And from B to B prime is 16. So we just subtract 16 from 32, and that will give us a length from this portion to that portion. So that will be 16 over 3.142 times the diameter, which is 3 squared, all on 4 times the modulus of elasticity for that material. Don't forget that this material was different from this section. So that is why it was given as 150 times 10 to the power 6 KSI. So we said that it's going to be times 10 to the power 9. Since the KSI is also times 10 to the power 3, add the power 6 plus the power 3 to give us power 9. And from there, we are going to get our deformation for that side to be negative 1.50, negative 1.509 times 10 to the power negative 7 inches. Sorry for that, since my pen is very sensitive today. Good. Then from there, we can see that the question was asking us to calculate the displacement at A. Quickly, let me explain that, and then we calculate our deformation, our displacement at A. Look at the diagram. Looking at the diagram, this is point A. All this side is assumed to be point A. So the movement of point A, you can see that it will be as a result of the deformation at section 1 plus the deformation at section 2 plus the deformation at section 3 is what is going to cause the movement of point A. So it's a combined effect of 1, 2, and 3. It is just at the end. So it is just like calculating the total deformation. So from there, we can see that the total displacement at A will be equal to displacement at A will be equal to that of AB, the displacement at AB plus the displacement at BB prime plus the displacement at B, the displacement at B prime C. Then we put all of them together. So the displacement at A is going to be 2.721 times 10 to the power negative 7 plus the deformation in the second section, which is negative 2.263 times 10 to the power negative 7 plus the deformation in the last section, which is negative 1.509 times 10 to the power negative 7. And from there, we can see that the deformation at A will be equal to negative 1.051 times 10 times 10 to the power negative 7 inches. And that will be the deformation at A. Let's look at the deformation at B as well. So I from the question. I from the question. The deformation at B is going to be, this is point B. This is point B. So the deformation at point B will only be as a result of the deformation in section 2 and the deformation in section 3. Because when you are moving from point C, which is now the rigid support, This is when you are going to move up to point B. So the deformation is only as a result of section 2 and section 3. So from there we can say that the deformation at B, will be equal to, as a result of B, section B prime plus B prime C. And from there we can see that our total deformation at B is going to be negative 1.509 times 10 to the power negative 7 plus negative 2.263 times 10 times 10 the power negative 7 as well. And our final answer is going to be negative 3.772 times 10 to the power negative 7 inches. Negative 7 inches. So that was pretty much simple, isn't it? So that brings us to the end of this question. We hope you understood the concept. In case there is anything you don't understand in what you have just solved, you can kindly let us know, and then we will be happy to assist you to be able to understand the concepts and how they are applied in solving this question. So thank you very much for watching and staying in touch with us. Kindly subscribe, like, share, and hit the notification bell. We are happy to have you with us. We'll end here. So we meet again in our next video. Bye-bye.